this one. Oh, apparently, I could have sworn I've had Zoom share my screen before, but I have to. Oh, I guess I upgraded Zoom and now it's confused. So 1 second here. And I should be able to share now. Okay, I'm looking at screen sharing stuff, and it is not. Let's see here. Hold on. Oh, I have to restart. I'll join again. That's the problem. I have to restart now that I've allowed it to do my screen. There now. Um, Fingers crossed. This one, share. Okay, I don't know why it's not letting me share my screen. Hold
There should be a green button in the middle
on.
under.
Hit that button, and when I select the window to share, it tells me that I have to grant permissions in system settings. I look at system settings. Zoom is on, like it says, enabled screen audio and audio recording.
This is Mac?
Yep, this is Mac.
Oh yeah, I have. I
Um,
will know soon enough because we're getting Macs. Yeah. I have Linux.
okay, let me try one more thing. Sorry about this. I was
Mm.
not expecting. Um, Man, okay. So let's complain about screen sharing. Great. Okay. So, yeah, this is a talk about an algebraic structure called Duoids. There's a library on Hackage called Duoids that's only gone up there recently. This is work that has been part of things that I've been doing for years. I had kind of parts of this a number of employers ago, like maybe I don't know how many years ago, but a few years ago. And then at a job after that, I kind of learned about what these are in category theory, with a little, a little more formalism than I had had up to that point, which helped me realize that I was actually looking at something real. It wasn't just something I made up, and like yeah, just kind of gave me some more guidance in terms of like putting something together that felt complete and useful and whatever. Um, Rather than just something ad hoc that I had been working with. So, Duoids is something that almost nobody seems to have heard of. There's not many papers on them. When I talk to people about them, they don't seem, like category theorists or otherwise, they're not like a very commonly cited thing, but there are some papers on them. And I found out that they happen to do something very, very nice for us in Haskell, as we often find with various categorical structures. But um, but so I just wanted to start here before I even talk about like what a duoid is, just like look at simple examples in Haskell, and definitely stop me, interrupt me if if anything doesn't make sense at any point, and we'll break it down. But these first couple code blocks here, right, are simple definitions with do notation, right? And they're, obviously not ones you would actually write. They're like effectively partially evaluated already. So like rather than having some expression that evaluates to write, we're just putting the write in there, and just so we can see exactly like, what's happening when we're using this notation. So in this case, we're just there's already a typo in it, I see, which is that this should be either list of string or string, not just string or string. But so I got one bug already in there. Good start. So anyway, simple do block, right? First, there's two values that are just, you know, right. They like succeeded, whatever what is evaluated worked, and we got a value out of it. And then we try to merge these values together, which fails. And so we get this, we get a left value, right, out of that. And if you were to evaluate this in Haskell, assuming the right types, the result you would get would be, this left. I guess you can't really see my cursor, unfortunately, but it's that left couldn't merge records X and Y, right? So that's like our failure case. Yeah, and that's what we get out of that first block. And so that's just, standard. We're using monads and going through this sequential do notation imperative style thing. Another, again, very similar example, except this time what happens is we couldn't find the values we wanted to look up, so everything fails, right? Or would fail, right? Because we have like anything that you try to do is failing. And if you're used to using either in a monad, you know that the result that comes out here is simply the first thing that goes wrong, right? This couldn't find record X. And it's a little frustrating. Like, this is definitely a problem that people complain about in Haskell a bunch. And there are various solutions to it. But like what people often want to have happen here is they're like, look, there's no dependency, right, between X and Y. They're two independent things. We try to do two different things. And then, sure, we want to combine them after the fact. But first, we just want to do these independent things. And if they both fail, we should have some information, right, that both of these things went wrong and not just the first one that happened to go wrong. And, in Haskell, this is commonly called validation. There's the either library that gives a validation type that's the same type as either, but with different instances so that you can get that sort of accumulation of failures happening, right? So then in that case, you can get multiple errors at once. But when you're using do notation and you're using either, you're just going to get the first thing that goes wrong. And if you've ever used a bad web form, it can be really frustrating when like something goes wrong, you have some error message in your web form and you like fix it and submit again, and then there's some other error in your web form. You're like, oh, I gotta fix that thing, and just kind of go through things one at a time, as opposed to being told like up front, here's 10 things that went wrong, let's deal with them all, and then we can get through it. So you can scroll down a bit to the next section there, Robert. So we're gonna make 3 little changes, or 4, depending on how you count, to this code that change things a lot. So the first is we're adding a couple language extensions. One here is called applicative do. We don't have to worry about exactly what it is, although it's mentioned in the comment there. And then the other one is called qualified do. Then we import this module, control duoidal, which is in the Duoids library in that package. And then the last thing we're going to change is where we had do notation. Instead of just saying do, we're going to say duoidal.do. So that's the only change to the body of our code. Again, we're importing and adding some language extensions here. And for that first case, right, where we have them succeed and then the second thing fails, we have the same behavior, right? Our result comes out, it's couldn't merge records X and Y. No surprise, either did exactly what we expected it to do. But then in the other case where we have the 2 independent inputs fail, right? We scroll down a little bit farther. So I have some exposition written in here, but there it is. So again, what we found before with the normal either was that middle couldn't find record X. But what actually happens now by changing it to duoidal.do, we now have a proper collection of a list of the multiple things that all went wrong. So we have that parallelism, or that this accumulation of errors worked for us.
Greg,
Yeah.
Is the bug because there are 3 things that went wrong. The first
Say that
one
again?
is there are really 3 things that went wrong. Couldn't find the record X, couldn't find the record Y, and couldn't merge records.
Oh,
right.
right. So no, there's
how
not 3 things that went wrong because those first 2 are independent. So we can do those without, we can just evaluate those. The third one depends on there being a X and Y having succeeded,
correct?
Right? So we only hit that last case when there is some dependency between the data, whereas the independent ones we can evaluate. And so, whereas before with just using either and regular monadic do, no matter what happens, just the first thing that goes wrong is what happens, is what you get as a result. But here, as long as we're getting, as long as we have things happening in parallel or independently of each other, we can collect those things and then,
Mm.
and so we say, here's multiple things that went wrong. And we never get to find out if the last thing would go wrong or not because we can't populate it with those values for X and
Right, right,
Y,
right, right, right.
right?
It's still sort of monadic
Yeah,
computation.
exactly.
You just accumulate the errors.
Yeah.
Sort of. Okay.
And so this, and so we can scroll down a bit more. So this is the change, right? The big change here is that without changing our code, I mean, we just changed that do to Duoidal do. Um, we let's see here. Yeah, you can go to what changed. Yeah, that's good. Where that headline is what changed can be the top there. Okay, so the three things that changed here. One is applicative do. So so do is just sugar, right, over regular function calls and stuff like that in Haskell. And what it does by default is something like this first block here, where it executes the first thing or it has the first expression, right? And then it uses the bind operator to bind it to a variable and then execute or to then evaluate like everything that comes after that, right? And then the second thing also then becomes the expression bound to a variable and again through. So you can see the sequentiality happening, like one, then this, and just one after the other. So what applicative do does is it changes that. It identifies where those things are independent, like our X and Y are independent of each other. And when possible, it desugars to using applicative operations like lift A2, um, which gives us that kind of independence. And normally, applicative do is of limited usefulness um, because basically, if you have any data dependencies in your whole do block, it will do everything monadically. And actually, it just depends on the instance on the type, really, because you can only have one applicative instance on a type, right? So either's type is is just what you're used to, right? Just the first thing that goes wrong is the monadic behavior. And with the definition, the way that Haskell defines the functor applicative monad type classes in that hierarchy, um, your applicative operations have to do basically the same thing that the monadic ones do. They have to agree. And so that forces so if you apply applicative do to either, it doesn't matter. Like it's just going to give you the same result as it gave you without applicative do. Now, the nice thing is you can provide a different type like validation, and then you get error accumulation, but that do block cannot have any data dependencies at all because if it does, you won't be able to use validation because there's no monad instance, right? So you're stuck in this place where it's like I'm either restricted to only using applicative stuff, or I'm going to get out the monadic behavior no matter what, even if am using applicative do and getting this more independent desugaring that happens in the second case. But in our case, as you've seen, we can take advantage of the fact that there are some parts that get desugared applicatively. And so the next piece is qualified do. Um, and both applicative do and qualified do, they already exist. They're like in GHC, they're very helpful things. What qualified do does is allow us to write that duoidal.do. And that's like a little bit of magic that says like if you qualify the do syntax itself, put some, module qualifier on it, then when it desugars, everything that it desugars to is going to also be qualified that same way, right? So you end up, when this gets desugared using the applicative do, we get duoidal.join, duoidal.liftA2, which means we're not just, do notation is no longer necessarily using the operations defined in base. It's using whatever operations are scoped with that name, like in that module in Duoidal, to desugar to. So that's what allows us to then not just use the lift A2 on either when like the one from base when we're using the applicative. And so now we can again desugar, just use regular vanilla either out of base. But the way that do desugars allows us to say that actually we want lift A2 to behave differently than bind and not to have that sequential restriction on it. And so those two things, those two changes are again already in GHC. This next thing, control duoidal, is what's new. And this is a very summarized thing of one piece of it, but just to give some idea. Basically, it's done by using new types, right? So in the case we are just looking at new types over either, right? So we can have parallel either and sequential either. And then a duoidal, the class duoidal, just expects both an applicative on the parallel version of either and a monad on the sequential version of either. Um, and so if we have both of those, that means that we have, well, yeah, assuming we follow the laws and stuff, we'll get to that. That means we can do all the duoidal operations. So when we use lift A2, it'll treat it in this parallel manner. And if we use, as you can see here, like basically the operations defined on duoidal stuff are just unwrapping the new types and wrapping the new types and then calling the underlying operator. So we call lift A2. We actually do just call base lift A2 because we defined an instance for either that behaves differently in the parallel way and the parallel new type than under the sequential new type. The sequential new type is basically always going to be at least very close to, if not identical to, the normal monadic behavior, the normal instances we have already for applicative and monad and everything. Um, and so, yeah, so what this lets us do, as I talk about, is like we get to, distinguish the applicative operations and say that it can actually be parallel, like validation, from the monadic ones that are necessarily sequential. And because base is kind of historically like monad and applicative, like applicative wasn't a superclass of monad, a lot of operations have had duplicate names that have just lingered around, right? So pure and return, like linters in Haskell will tell you to replace return with pure. And then these operators here, it'll tell you to replace the second one with the first one, those little star arrow and arrow arrow, because they're defined to be like, they have to have the same behavior, except that the second one in both of those things is constrained on monad, where the first one's constrained on applicative. So you might be able to weaken a constraint on a function if you're using the first ones instead. But since those names exist and there's this redundancy, the Duoids library actually gives them the distinct semantics. It gives pure and star greater than the parallel applicative semantics, and it gives return and double greater than the sequential monadic semantics. And so, we saw that simple example is how we get some parallelism. And of course, there's a type class here. So you don't make a type class unless you have some flexibility, right? Like we can find other cases where the same thing shows up. So that's, so yeah, so let's scroll down a bit more and we can see like the next thing that shows up is IO. And so in IO, we have the same kind of thing as this. There's an async library out there that has a bunch of tools for doing, asynchronous stuff. So you can do IO in parallel, stuff like that. But in base, you're just kind of, again, doing things monadically. You do IO in do notation, and all of your things happen sequentially. You want to read multiple files. It's going to read one and then the other. And then, and this is, again, very similar do notation, but more IO based, where like we try to read two files and then we try to, do something with them and write the output. And again, with just regular do notation, it's going to be very sequential, right? Every step is going to happen in order, one after the other. But again, just by adding our duoidal to the do notation, we now get parallelism where possible. You don't have to change anything about how you wrote your do block. It can all be just as sequential looking as it ever was. It can be in whatever order. Applicative do handles extracting that possible parallelism out of it, and then we take advantage of that to use a parallel implementation where we do have that independence. And as it's right below here, this shows up other places. Transformers, except T, of course, is very much like either. And Raider T is another case that shows up, and I'll talk about that a little bit later. And then this next bit is the laws. So, there are, of course, with any algebraic structure, there's certain things that have to be true. And these are the laws that hold for specific reasons. Basically, the relationship between, so what a duoid is it's a particular relationship between two monoids. And now, we've been talking about things like functor and applicative and, monad. But those things are, or at least applicative and monad are monoids, right? We don't have to worry about why right now, but they're just monoids in a different category than the Haskell type class monoid. But this is so talking in a category theoretical sense. There are two monoids that have a particular relationship with each other that's defined by these laws here. And these are all just natural transformations that we have to be able to convert the unit of the parallel monoid to the unit of the sequential monoid. We have to be able to take a parallel composition of two sequential units and unify it to a single sequential unit. Do the opposite, take one parallel unit and make it a sequential composition of two parallel units. And this interchange, which is like the kind of somewhat complicated one, but what it basically says is we can take parallel composition of sequential, of sequential operations and turn it into a sequential composition of parallel operations. It just has to rearrange those in a certain way. So you can see here, like A is the first operation in one sequential thing, and then C is the first operation in the other sequential thing. And then the result of the natural transformation says we can run A and C in parallel. Then when they both complete, basically, we can run then the second parts of those two in parallel. And that sort of defines that kind of relationship between sequential and parallelism.
Wait, Greg,
Yeah.
is the pipe like honest to God operator? I mean function,
No.
or
This is
this is just
this law thing is just just trying to
okay.
be somewhat clear. Yeah.
Yeah, okay.
Like the three dashed arrow is just like I'm saying this is the natural transformation from this to this, and
Yeah,
then the triple greater than is like that's a fake
got it.
sequential
Got it.
sequencing operator versus the pipe is the
Yeah, yeah.
parallel one. Yeah. So okay. So we've seen a bunch in the category of endofunctors, right? Which is where we have applicative and monad instances. They exist in plenty of other places. One of them is just in regular Haskell, like so proper types, like where you'd actually have an instance of monoid. So there's this great library that I'm a big fan of, algebraic graphs, which is algebraic, like an inductive representation of arbitrary graphs. It's pretty neat. But this very simple data structure, their graph data structure here, just has an empty graph, a single vertex, an overlay, which is two independent graphs, right? There's no edges connecting them between two. Yeah, so it combines two graphs, right? It's a recursive structure. And then this connection, which is creates an edge between all the vertices in the first graph to all the vertices in the second graph. And so that's this graph data type that's used to do an inductive definition of graphs. And it turns out very nicely that this is a duoid itself, where again, we have two monoids here. So we have two units. They happen to be the same in this case. They're both the empty graph as the unit. And then our parallel. So these are the actual operators, Robert. They're not great. I mean, I don't know. I don't have. I feel like I'm always struggling to find obvious operators. But anyway, parallel composition is written as this like two pipes with a dash between them. So kind of like the OR operator. And then this arrow with a line between it, greater than line, greater than, is the sequential operation. And so say here, like this graph is actually the free normal duoid, and versus, so as I mentioned, a duoid has two monoids in it. A normal duoid is where the two identities for the monoid are isomorphic. So like in this case, we can see like they're both actually the same thing. So trivially isomorphic, they're just the same identity.
So
And
so quick question. So this is
yeah.
this is the directed graph, right? It's not the graph. It
Yeah,
has
so this
it
graph
has
data
a
type isn't necessarily directed, but there are like in that package in algebraic graphs, there are both directed and undirected classes and
mm.
instances for all those things
Oh, I
to
see.
do that. Yeah. Um, but yeah, so anyway, this is a nice thing that it just turns out to be a free normal duoid. It just maps directly to duoid, so we can just like lift any type A into a duoid with this the same way you have like list being the free monoid and non-empty list being the free semi-root. So those are just kind of nice parallels between data structures and these notions. Um, and so, yeah, so as I mentioned, yeah, when the two identities are isomorphic, it's a normal duoid. Um, and I do distinguish that in the package, but it's often we don't have to think about it too much. It just kind of works. So can you scroll a little bit more? Next section here. Okay, yeah, another simple case is the max plus duoid, where the parallel operation is max. Um, and so the identity for max is the minimum bound on some type. And then the sequential operation is addition. Um, so if you're thinking in terms of graphs, I mean, not that you should, but this is, this would be undirected because there's no, it's like commutative. So yeah, so again, simple instance, there's nothing to it. Min bound with max and zero with plus for your two monoids. Um, and now I mentioned writer T earlier, or writer. You can do some neat things with writer when you're using duoids. So like here is a block of just, a mix of independent and dependent things. Each one is annotated with like a name for that particular step, whatever it is. They all have a tell that says like, hey, label this action this, right? So then when you evaluate this, you get a structure, looks like this, which has the results here in our tuple there, and then it has the writer value, this graph that we've constructed, right? Because this is using that graph type from algebraic graphs, where the vertices, so each of these labels of the vertex. And so as we go through this sequential thing, well, what looks sequential, and the parallelism is pulled out, that is maintained in that graph structure. And so that diagram here at the bottom is actually the graph you get out of that's like what the writer value is. So you can actually get this drawn graph out of, I mean, like, using dot or whatever you want to serialize this graph structure into. You can render a graph like this that shows exactly where the data dependencies are in your operation. Because right, like one of my complaints with do notation has always been that like it hides the actual data flow like through whatever series of things you're doing. It just looks like one thing after the other. It's not clear like if you can change things around, what's like works how. And so now using this and this kind of annotation on it, you can extract, you can like recover that data, that data dependency stuff and try to figure out like what other benefits you might be able to get out of it. And of course, just the instances on IO and everything like that, you don't have to think about it too much. You are actually getting that parallelism as much as possible. You don't have to be like, oh, actually, I should turn these multiple things into, like a validation and then combine them this way and then like do the next step. And, because again, it discovers and extracts all that for you so you can actually get the maximum independence possible, and again collect, whether it's collecting all the errors for different, like the parse phase versus like different phases of your compiler or whatever, right? You can not just report the first error you come across, or if it's again parallelism through IO for making things more efficient or whatever different things you're doing. And using writer like this is nice that way. I didn't put it on here, but you can also use like writer with any duoid, right? So you can use the same max plus one. And so say like your actions each have some cost. So instead of annotating them with like a label, you can just give them a value that is like represents like, how expensive that, or like, I don't know, some cost in like the operations you're doing. And then the result that you would get out of that would, get the max of all the things that can be done independently, right? So if you can do four things in parallel, like it's going to say, and like one of them takes 5 seconds and the others all take 2 seconds. Well, to finish that, it's going to take 5 seconds, right? Because it just is like whatever the longest one takes. Um, but if they're sequential, you have to add up those costs. And so that max plus duoid handles that, right, automatically for us. We just are using a number in our writer, and anything that's independent, it's going to take the max of those values. And then as it gets to the next step, it's going to add that value to the result of the next stage. And so at the end, you get a cost that is kind of that optimal cost of if you did all these things in parallel and the required things sequentially, that's like your cost outcome of that. And again, just using writer. So is everybody on board with where things are? Like, is there anything that I should go back and explain or justify or anything that I'm stuck on? Okay, great. Then let's,
I have a question.
yeah.
Oh yeah, this is kind of a weird question. I wonder if this could be like more dependently typed in a way that you say annotating stuff, yeah, and you want to
Hold
have a
on
total.
one second here. All right. Oops. Okay.
Yeah,
Back again.
this would be harder because that would require much more flexibility in the do's. But that's like ideally what you it would be fantastic if you could annotate maybe cost functions in a way that you want to have a compiler guarantee of total cost, not extending 300, right? Um,
Yeah. So I think that actually brings up a good point. So I mean, I definitely, I'm like showing a lot of stuff in this do notation because it does do a bit of magic for us behind the scenes with the desugaring. But this is just a regular library. It does just provide operations like bind and things like that or whatever. And yeah, definitely like having yeah, dependently typed version of it. I would be very happy to see, yeah, like where else it comes up. And just kind of in this in the almost the vein of dependent types, or moving that direction. Just go down to the next section there. So this other category, right, is a category from it's a category of of functors from the category of endofunctors to constraints, which is the category that contains the actual classes monad and applicative themselves. Like, so not instances of, not things that have instances of those classes, but the category that contains those type classes. Um, and I have some other library called Haskell that does crazy category theory, like category polymorphic stuff. So you can actually just like treat type classes the same way you would treat like other values and stuff like that, and do kind of neat categorical stuff with them. That's not implemented here, but just as a neat side thing, applicative and monad, the classes themselves actually form a duoid between them, a normal duoid, where yeah, return and pure, those operations are the identity, um, and are actually not those operations, but the types of those operations are the identities, and the same for bind and lift A2, or join, sorry, join and lift A2, not bind. Um, but anyway, it's just like an interesting thing that it's that not only do we see this duoid show up between a monad instance and a separate applicative instance, but actually the applicative class and the monad class form the same relationship. So it's neat to see that just happen in different layers, I feel like. Um, anyway, like I said, maybe I didn't even say, this structure I feel like is pretty simple. Um, and some stuff here is a little like, I don't know, maybe not that simple, but I feel like using it, like I mentioned, you like minimal changes to your code, you can start taking advantage of just kind of magically getting things like accumulation of errors and things like that without having to do what we typically do, which is like if you're doing that stuff, you're doing manual conversion between different types to get the different behaviors out. Um, and this requires not changing any of your logic. You just replace, where you had do with duoidal do, and you're now getting this more general behavior. Um, and so this has been super helpful for me. Like everywhere, I use this everywhere now. Like it's just because it solved that problem where it's like, oh, whatever, I'm just going to return one error at a time. I'm not going to worry about it because I don't want to think about doing anything else. Or taking that step and be like, okay, I'm going to try and like report errors better or whatever. This again does it magically without having to change your code, without having to change the business logic or whatever part of your code. And so uh, sorry, somebody have a comment?
I have a question. Yeah,
Yeah.
might be. Yeah, and feel free to answer later if it's. Yeah, basically, I was wondering if this has any relation with the selective applicatives.
You're
I
not the first person to ask that. What makes you ask
okay.
that, first of all? I'm curious.
What makes me ask? I've read the paper about selective applicatives. I've not fully understood every single detail of it, but surely they have to do with the fact that essentially when you have like monadic do has to do with like sequential way of doing actions, right?
Mhm.
And that also makes it more difficult for you to make static analysis on that type of program. And applicative instead gives you this parallelism in the sense that you can do the actions in parallel because they have nothing to do with each other, right? And selective is something in between. And since in this case as well, you're talking about something in between alternative and sorry, applicative and monad, that makes me, yeah, it makes me think of that, even if
So
I've not fully understood it, but
no,
I see
that's
some
great.
relation.
So I haven't explored that relationship yet, but it's interesting because selective applicatives were, I think, um, created or whatever, implemented by Andrei Mokov. Um, and he also has written about this concept called united monoids, um, which he has only written about them in, I think, in the category of Haskell, so like where monoid is actually a type class. Um, but uh, but so he's also the author of algebraic graphs, which is one of his examples of united monoids. United monoids, I think, are um, a subtype or whatever of duoids. Like they are more restricted. Like there's more laws about them. Um, and so so basically like his graphs are his united monoids and they're duoids, generalized to duoids as well. But I don't think Andre has has explored the relationship, only because I mean I've talked to him a few times about both of the like these various things. And so since that hasn't come up between us, I feel like he hasn't, but also because selective applicatives operate in like where I kind of started here, right, with applicatives and monads, but all of his stuff about united monoids is about like monoids and semigroups. And so I think that distinction has like not necessarily popped up. But anyway, you're not the first person to ask me if there's a relationship there. I have not taken any time to explore, but I definitely wouldn't be surprised. And it is interesting that like, yeah, Andrei Mokov is like involved in both of those things. So yeah, I do want to look into that, but I have not had an opportunity
Thanks,
to
but
yet.
knowing somebody else asked about it makes me feel like I've asked something that is not
Well,
completely
that's great. Yeah.
related.
So yeah, so the last thing I want to mention here is that like I get a lot of use out of this just on its own. Um, but I've taken this a lot farther. It's unfortunately not yet been published on Hackage, but I have kind of extensions to this that if you scroll down a bit farther, yeah, that's good. At the bottom, I think. So we have, if you look at this little diagram here, the duoid on the right is like these four operations on the right where we have, we have the monoid for monads, which is return and join, and the one for applicatives, which is pure and lift A2. And that forms our duoid. And and then we can kind of extend it with another monoid, which is commonly implemented as alternative in Haskell. And then there's monad plus that combines alternative with monad already. So basically by taking that group of two and adding this third to combine the duoids and the lattice idea, we now have a notion that the alternative gives us a notion of or. The parallel duoid half gives us a notion of and um, and the monadic one gives us again the sequentiality, right? So not only do we have this like these things are happening in parallel, but we also have like we only care about one of them succeeding potentially or things like that by adding in the alternative case. And so I've been working on this thing for what I call beautiful failures, which is a very rich way of handling errors that is invisible, like you see here with the duoidal do, how you don't have to change the business logic to get richer error handling out of it. Um, but it handles the alternative notion of like, oh, that failed, but then this passed. But then if all of them failed, typically you just get your final error, right? Like when for either, it goes through all of them and it's like, okay, here's the last thing that went wrong. And it's like, well, if I fix any one of those four things that went wrong, I would succeed. So why am I only getting a report about one of those things that I could change, right? Um, and so that gives us this notion of like having like of errors where we have to fix all of some set or some subset of them and combine. So we get like that sort of thing. And then we also have a notion of implication that I added on here. So you get very close to a Boolean algebra, but you don't have an excluded middle. So you have what's called a hating or hiding algebra. Um, and so anyway, all of this together, so implication in a sense of error handling is sort of like relationship of like, this kind of caused or like is related to this other thing. So parts of that are like various contexts, like stack traces that get attached to errors, like that call graph. And then also you can attach arbitrary other data, not just the call stack to things. And so this uses as a basis this Duoids library, but then extends it to give us, again, much richer error handling where we can effectively group errors. And so, you get like, you compile something and it spits out 100 errors and they're all like the same, or like there's some typo that it complained about early on or whatever, or like gave you a warning about, and then like all this other stuff happened as a consequence of that, basically. And it can handle, not perfectly, but they can handle grouping a lot of that stuff and kind of hiding those things and say like, hey, I'm showing you this one error that we think is maybe behind these 100 other errors that happened. So like fix this one thing and don't bother reading through 100 things that went wrong, And so the idea is to like make it, one, easy for developers to collect lots of, information about what's going wrong. But two, when you do that, like what tends to happen, right, is like what happens with compilers all the time. They just spit out a ton of errors, and it can be hard to know like what you should be paying attention to. And so with that implication operator in there as well, it kind of gives you some prioritization and ability to say like these are the things that that you should probably be looking at first, and so then reduce the cognitive load of the user, who's trying to understand these errors and how to fix what they're dealing with. So this anyway all works as like a library to hopefully invisibly to developers, produce better errors that are more complete and also easier for the users to understand. So that's kind of the layers on top of this Duoids library. But again, I use Duoids just in anytime I use either, which I use either in everything. Like I don't know anything that doesn't involve either. So so yeah, anyway, that's the thing. And definitely if anyone has questions or whatever, again, this code is released on Hackage. And so any issues that people have using it, I would definitely love to hear about too. Anything to shake out the things that I haven't run into. But yeah.
Thanks.
That is really interesting. Yes, it looks like it's addressing some of my peeves for sure.
So, sorry, what was that?
No, it's very interesting. So it looks like it's addressing some of the pain points that I have
Oh, good. I mean,
encountered in
yeah,
my programming. Yeah.
definitely it addresses my pain points. So I'm hoping that those are pain points that, more people have.
It addresses them in a very elegant way, as opposed to like sweat and brute force.
Right, exactly. I mean, that's what I mean, I work on compilers a lot. And that's where like I was always fighting with that sort of thing because you do want to, present more information than like one thing. I mean, I deal with plenty of, people write a language that's got some neat things or whatever, but like it just like says, oh, this one thing is wrong. I'm like, oh, okay.
Well,
Oh, now there's one more thing wrong. And
also,
I'm like, oh,
it's also
frustrating.
like a promise of using alternative in a way that is um
Right, yeah,
is positive. Like it's not hiding errors from you. It's more like trying to expose the information.
exactly. Yeah, this is exactly
In
what I was thinking of when because you brought that up during Nick's talk, I think is when you brought it up, right? And like the issues of dealing with alternative.
uh,
And I was like, no, there's like good, we can do good things with it.
I have been just there was a lot of pain in the code
Yeah,
I have been maintaining, basically rewriting something with like better alternative, right?
yeah,
Which doesn't suppress errors. But
yeah,
yeah,
exactly.
um um that yeah, that is like super interesting. And only there's some mathematical structure which combines hiding algebra with the Duoid in some interesting, meaningful
Yeah, I mean,
way.
I wonder, like I said, there's
Yeah,
not that much on Duoid, so like,
I
it's just and maybe I don't know if it's just not as, if category theorists just don't, they're not dealing with concrete errors in programming languages and stuff like that. Like, I don't know if they're not finding things that it helps them think about. But definitely when I came across this notion, which I don't even remember how I first, found the right page on NLab or whatever. But
yeah.
when I did, and I was like reading it, I was like, wait a second, this is that thing that I've been like hacking together and like pretending as a thing, and it turns out it's a real thing.
So
Um,
before the meetup, I started Googling because I didn't know what Duoid is. Uh, so I got on NLab as well to just see like very dry, very short
right. Yeah.
page, right?
Yeah.
Uh, and then like, okay, so Duoids in programming. And Google instantly just gave me droids in programming.
Right. Right. Yeah. There's nothing. There's nothing out
And
there.
there's like an option, show only Duoids in programming. So I click on it, and still gave me droids in programming. So I done like in quotes, the no Duoids in programming, and then it told me that there's no such
There's
thing
nothing.
really.
There's no such thing. Yeah.
No.
That is correct.
So yeah,
Um,
it looks like there should be, right? Because it looks like there is
yeah.
some good
And
story
again,
here.
it's the kind of thing that people have come up with different solutions for over time. I mean, I think that I mean, granted, I wrote this one. I think this one is the most elegant and like nicest way to do it. But I've definitely, long before I knew about Duoids, been frustrated with like the annoyances of trying to put those pieces together, and seeing those same parallels, haha,
Yeah,
in both like error handling and IO, and like where else they can crop up, and being like, there's got to be something here. So yeah,
yeah,
it's
yeah.
and like I mentioned, Andrei Mokov calls them united monoids, or again calls it a structure that I think is just a more restricted form of duoids, united monoids. But so it's not like they haven't come up at all. I mean, and again, and even validation or concurrently in the async library, they're all attempts at doing this thing. But it's kind of like how when you're a Haskeller and you see, you think of a monad and you look at another language and it's like, oh, you just have like a sequence of statements, or you have your, yeah, your error handling or whatever, and everything is done per, situation. And we have this nice generalization. Here, even the Haskellers have been like kind of doing it ad hoc for, oh, here's how I kind of do this in error handling. Here's how I kind of do it with IO.
Mm.
Um, and so to find that there is something that gets us the same kind of generalization as we get from monads, um, for this kind of thing is really nice and really exciting to me. And again, it's very simple. I mean, the library is not complicated code. You've seen kind of how the things build up here. I mean, I'm leaning heavily on the applicative do and qualified do, in there. I think the applicative do is a fairly complex implementation. There's definitely some bugs in there. Like there are certain things that if you um, do them wrong, then your code just won't compile. And nothing to do with the duoid stuff, but just applicative do. I think it's just hard to identify some of, because it's looking through the sequential stuff and pulling out, doing the hard work of identifying the parallelism basically. So
So
I don't have to.
I'll send the link. Hopefully, this record to Jason. So like we internally had this problem because we had this like a logic solver which ends up I don't remember my talk, but and ends up calling different atoms, right? And tries to just assemble the results based on different ingredients, so to speak, right? And it tries to
Mhm.
do that as parallel as possible, but not too parallel, right? Maybe if you have some sequentiality because you need an input from the previous call, then you need to wait. Otherwise, tries to
Mhm.
parallelize them as much as possible. And Jason came up with this concurrent-ish if basically develop, but not in this generality. Develop something that done it
Mhm.
sort of automatically, right? By utilizing Haskell. In some of the interesting way, but this is like if you see this, it would be like, wow, I could have done that, right? So No, I'll try to. Hopefully this records.
Yeah.
I'll send him a link. Yeah, that
And
solves so many problems in an interesting way.
cool. Yeah, I hope so. I hope this is really useful to people. Again, it's very useful in the compiler world. Like, just because you deal with so much of, presenting errors and collecting multiple errors and stuff all the time, it just simplifies a ton of stuff. And I think, yeah, it can be so to people outside of that area as well. But I didn't, so something you just mentioned there, where you're kind of as parallel as possible. I touched on this earlier, but I just wanted to mention again that we're kind of reusing the names. We're reusing the names from base, like return and pure and all that stuff. And so while the do notation, we'll do that like as parallel as possible, basically approach. You can, use like what's a good example? Like there's not well, like that star greater than sign versus the greater than sign. Like if you are trying to force some sequentiality where there is no data dependency, like if things are,
Mm-hmm.
ridiculously parallel and you're like, we need to
Yeah.
not like start a million things at once, you can just use those operations that are constrained on monad, or that from the base versions are constrained on monad, like the double greater than, and force it to, even though there's no data dependency, to still treat it as a sequential operation. So you have that choice, so you're not kind of stuck with with like rolling your own if you are not doing the most parallel thing possible. It still just kind of does what you want to do, and you can be selective about that. But maybe not selective applicatives. I don't know. But yeah. So yeah, I hope people have a chance to try it out and use it. Raymond, you should definitely mention it at work.
Yeah. So Jason is no longer working with us, unfortunately. But yeah, I'll send him an email with that.
Yeah, right. Yeah.
Yeah.
Yeah. I haven't talked to him in a while.
That is really interesting. Yeah, it was that like the tendency of showing stuff that is like I really need to work, which is
Great.
uncanny. Yes.
I mean, the thing I love about this is I feel like a lot of stuff that I do or show is complicated, and this just feels so simple. And if any Haskell looks at the code, I think it's very straightforward, what it does. And if it's not, I would be happy to do what I can to make it more so. But whereas like things, like when I talked about like categorifier or things like that, like compiling the categories work, like that's just complex. Like there's no way around it, at least as far as I've discovered. And so yeah, anyway, it's nice to have pieces like this that can be extracted and made useful to lots of people without complexity, I think. But let's to transition to complaints a bit here. Maybe it's not a complaint now, but definitely one of my complaints when I was first dealing with this notion and wanting to like encode something like this was that functor applicative monad hierarchy, where like there's subclasses of the previous ones. So applicative is a subclass of functor, and monad's a subclass of applicative, because that meant that when I was first exploring this, that I couldn't create an applicative instance that did not behave the same as the monad instance without breaking like various laws and assumptions and behaviors. And that's exactly what I was trying to do, right? I was like, no, I want applicative to be this other thing that like behaves in this parallel way, and like monad to be that thing. And it's really too bad that, I mean, it wasn't even that, I mean, well, I guess it's been a long time now, but it feels like not that long ago that type class hierarchy was, codified. And it's like, oh, if only I realized this stuff before that, maybe would have landed somewhere else with how these things all get put together. But anyway, that historically has been one of my complaints, is that type class hierarchy. And yeah. So a transition to I think you can stop sharing the screen now. I don't
Yeah.
that link points to my repo. It points to a branch. I'll merge the lightning talk into the main branch soon enough, but I was just doing it on its own branch. So but yeah, that's there. And again, packages on Hackage. Please complain about it. I really like complaints. One, it means things are being used, and two, I can make things better. So I thrive on them. But yeah, so what else do people complain about in Haskell? What Haskell stuff is, even if it's not, I mean, it's fine if you're not sure if you're just doing something wrong. That's a good enough thing to complain about if it wasn't clear enough what you should have been doing. But yeah, anything in Haskell that's kind of been a pain in the butt.
Let me go because I decided very much related to talk. So my big pain point has been kind of error handling in Haskell, right? And if you try to do some historical research, like go to older version of libraries like ASON, even servant libraries like servant multiport or something, and you look at earlier versions, they're awful as far as error output. They overuse maybe, like maybe is their kind of like,
Yeah.
if something goes wrong, you get nothing. And this is by design. Don't expect anything else, right? And I was thinking why this is the case. And okay, I need to kind of decline this again. Um, the I was thinking why this is the case. And one explanation is like if you look from the kind of at the programming through a lens of uh, mm, uh, c- you know Kerry Howard isomorphism, right? You want to think about programs as proofs of sorts, right? You look at this in a very static way, and like the dynamic error conditions are really something you care about at runtime more.
Right.
And the main reason I think is this functional program became like it attracts people who are very much interested in mathematics, and mathematics doesn't just have in a straightforward application of mathematics, you don't get the you don't get the you don't get errors exposed in your reasoning.
Mhm.
They're more like falsehoods, and falsehoods are not relevant. You don't
Right.
care why
Like
things is
not
not true.
distinguishable. Like you just like care that it's
Yeah,
not true. Not you don't. Yeah.
yeah. Um,
Yeah.
but this sort of gives a more mathematical background to uh, to uh, to like how do you want to look at this, and that's really nice because maybe it's going to get traction, and people who have this mindset are going to say like, hey, well, that's a good mathematical model to think about computation, right? Mm. That's super exciting. So yeah. Well,
Cool. I maybe there's something that um I maybe maybe this is a complaint, maybe it's not. I'm not sure if it's a complaint or just a question, but I waffle a lot on using maybes because when there is basically like one way that something can go wrong, and of course sometimes you use maybes, it's not even that something went wrong, it's that there's no answer, like it makes sense that it's an absent thing.
yeah.
But definitely when things fail, if there's like one way to fail, rather than making all these kind of like you know, unitary error types that don't combine with other error types or anything like that. Anyway, it's easy to just use maybe as like, and it's like, oh, if this fails, this is the thing that went wrong. There's
Mm.
nothing else that can happen, right? But the problem is, or one of the problems, is that what you really want to have happen is after you get that maybe back and you're combining it with other things, and you actually have multiple things that can go wrong because you're dealing with multiple functions that return maybe. In each one, its failure means something different. Um, you kind of have to like, okay, now I have to build up an error type and convert them all. But the easy thing to do is to use the maybe monad, which just collapses them all together. And now you no longer
Yeah,
have
yeah,
this
yeah,
like
yeah,
this
yeah,
case,
yeah,
right? Where it's like, oh, it only meant one thing here, it only meant one thing here, it only meant one
yeah.
thing here.
I,
I did
uh,
the obvious thing and just combined
I,
the monadic
I
combination.
definitely see the code base I'm maintaining and I'm rewriting all of this. Yes.
Yeah.
So there are obviously existing combinators for dealing with this, but to be very explicit, I wrote one that I'm encouraging to use. It's called explain, which takes a
Mhm.
maybe an error message and it returns an either,
Really
right?
either on that. Yeah, yeah.
Yeah.
That's a good name for it too. I've seen it called like note. in some library. I don't know if it's like extra or
Mm.
either. So, but I like the name explain. I feel like that's a much better name for that. Um,
There is recently been a discussion on. I'm not sure I followed entirely like the point you were making, but there's been recently a discussion on Discourse Haskell about is the maybe monad instance ever good? Uh, and actually, yeah. So no, and the reason I'm mentioning is that because all the time we've been talking about it in this few minutes, I've heard always talking about error, like maybe as an error, something that
yeah.
maps to a kind of error. In reality, I have an example which I put as the last comment. You can see in that page I've
Yep.
linked in the chat, and that's actually the way that in the C++ code base I was working on, comparison and text diff and stuff like that, we would use std optional in C++, which is fundamentally the maybe monad, and we would use that not to map. It would not map to an error. It would just map to the natural missing of an element in a kind of two-way table with which you show insertions and deletions between two files. And in that case, like there is no other better type than maybe itself, because there
Sure.
is no information about the fact that there is something missing there.
Yeah.
Yeah.
But are you're not using the monad that's really there, are you? Like
Well, yeah, okay, I see what you
that's
mean.
the
Yes, that
yeah, I
is.
feel like that's when you start combining the maybes into one maybe, and you're like, oh, well, wait, what thing was
Yes.
missing, right? That's when you start like wondering about. But yeah,
Okay, I
in
see the
this
point.
case, I think this, yeah, maybe is definitely a very useful type.
You mean that this is a use case for the type, maybe not for
Yeah,
for the fact that it is a monad. That's irrelevant.
exactly,
Okay, I see.
exactly.
Okay, thanks. That I didn't think of that. Thanks.
Yeah,
There is something uh, deeply psychological about Haskell programmers, and maybe I think. So I've seen examples where people were doing extremely sophisticated stuff. And if you just look at this, like common sense is like, it doesn't make much sense. So including about maybe monad in particular. So I've seen situations where we use this HKD pattern, where allows you to kind of, uh, you know, like you do you enter a form, and if you miss a field,
yeah,
you get, well, you get nothing. Why not get an information which field form you didn't enter, right? Um, uh, it's like you do something extremely sophisticated, and you just forget about, like, okay, what I wanted to get out of here is an error message.
yeah.
But you're super happy that you automated a form creation, but you're getting it with a maybe. So kind of weird, right? It's like this is what's happening. It's again something to do, I think, with the kind of attraction to mathematics and ignoring the failure as not important.
Yep.
Mm.
And I mean, I agree. I feel like I'm always modifying code bases to like, yeah, remove maybes or add just better error types, some types in there. Because also it's very common to do strings, which is fine in some cases. But I mean, I definitely love to deal with the, actual algebraic error type that I can like, actually care about program, like do some, figure out what went wrong and decide if I need to retry or do other things. Like, just stuff about it. So I do a lot of like, yeah, retrofitting that stuff into code that exists. But it is frustrating too, because you often have, I mean, it's tricky. Like because we don't have like, open variants or anything in Haskell, right? Where you can just like add cases to an alternative, right? Like where you have a sum type and just be like, oh, I just want more cases. So if you have like different functions that can return, take an error in certain ways, right? So okay, I have nice small error types that handle like these few cases, and then as like I combine the results of those functions, I now have an error type that contains those error types, and you end up with this kind of like nesting of your types. And then the other thing that people will do is be like, actually, you know what? I'm just going to pretend all of these things can fail in the same way, because it just like I'm going to aggregate them all anyway. So I make one large error type. But if you're actually like looking at any of the functions, you can't tell. It's like, wait, can this error actually happen when I call this function? Well, no, it can't. It's just like we're just saying everything can fail in the same set of ways, and kind of lose precision there. But I mean, I don't know what the solution to that is in Haskell. I mean, really in general. But I mean, there are things like having an open variant where you can just kind of combine. those alternatives and say, oh, now I just have a bigger alternative that has, 6 cases instead of,
Mhm, mhm,
two that have three.
mhm.
And so, yeah, when you can do that kind of stuff, um, because I've done that in C++ a bit, which is with like, STL stuff, you can kind of do some magic with variants there um, to kind of basically do some like implicit conversion that will turn a small variant of like 3 error case or whatever into like a larger variant because it has those subset of cases are in both or whatever. But anyway, so there are different ways to handle it in different places, but Haskell, it's always kind of been this, either you create one large thing and just return types that where you can actually have most of the error cases happen, or you break it down and you end up with these deeply nested error structures, which is what I tend to prefer. I try to do precise errors on different things so that when you call them, like these are the only things that can go wrong here, which is also good for then letting you know when you've eliminated all possible you know situations where a particular error happens. And you're like, I can just delete that error case now, great. Which is harder when you're already like returning it in places where it can't happen.
Well,
So anyway,
you can play some games with like extensible the sums kind of approaches, right? Where you're saying that
you're right.
you want to have well this field is a member of sorts of a
Yeah,
larger error is one of them, but you
yeah,
don't
you're right.
specify
It
the others,
is.
right?
Yeah,
You
it
can
is.
play
There is often a
uh,
question too about like, oh, what dependencies am I willing to bring in? How much
there,
complexity? Like there's all that
there,
kind of stuff. But
they're
yeah,
not
you're
super
right.
easy to deal with, but there are definitely ways to sort of try to do it more polymorphically, so to speak, right? But
Mhm.
yeah, um, I end up probably not doing it and like writing types and then maybe converting them to error types and converting them. Yeah.
Yeah, I feel
There's
like I spent a
also
lot of time thinking about error types and
there's also a
never happy. But
tendency to use strings in Haskell for errors,
yeah,
and that's somewhat disappointing, obviously.
yeah.
In the ecosystem libraries, right? Yeah.
I definitely am not a fan of that. I mean, I like, like being able to do things. You have multiple errors that happen to be the same error case. Maybe they happen in different files or different, source locations, and being able to say like, hey, this thing went wrong. It happened here, 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 and here. Like you
Yeah.
can't do that if you're like dealing with strings, you have to,
Yeah.
you can't like, and also, I mean, just strings, they're plain text basically. Like even something I've definitely dealt with in the past. And this is actually a separate aspect of this beautiful failures thing, which is dealing with like, yeah, like structured error serialization. Because it's like if you're just spitting out something on a command line, like that's different than if you're like having like a pop-up window in an app where you want to like format some error or display some things or have some like real references where it's like clickable and take you to the right place versus like plain text dump out. And so if you're just doing strings, you like lose all that kind of flexibility to do any kind of like formatting with it or like anything rich. So yeah, it's and you never know if if you are trying to like match on strings and then do stuff about it, you never have any sense of like, am I covering things? Am I like missing these cases? Um, so yeah, I do avoid those as well. Anybody else have any complaints? Anything that they don't like about Haskell? It's just perfect.
There are not enough jobs.
Yeah, that's right.
Yes, that's very true.
That is a serious Haskell problem for sure.
Oh,
Yeah.
okay, correct. There are not enough jobs in Europe.
No, it's true in general.
Yeah,
But it sort of means that Haskell doing something right. So I strongly believe
Yeah, I
in
agree.
this thinking, right? That that uh, popular means incorrect. There's no such a thing as well done and popular. If popular must be screwed up in one way or the other.
I agree
So
with this.
yeah, it's
The
necessary
world runs
condition.
on JavaScript. That tells it everything.
Yeah,
right.
to be right, the necessary, not sufficient condition is not being popular. Yeah.
Yeah, I mean, it is frustrating the Haskell job thing because there was a period where it was looking very promising. There was like a lot happening. I mean, Boulder was somewhat of a hot spot, as small of a place as it is for a while. Um, then various things, including COVID, but not only, have um, made companies disperse. I don't know. Plenty of companies have. I don't know what. I mean, definitely some companies have just disappeared. Other stuff has been like, we rewrote things in Rust for some reason, things like that. But I don't know. Yeah, I don't know what it is. I mean, definitely there's still companies out there. I mean, like Mercury, for one. And yeah, I think one thing too is that Haskell got eaten a bit by the blockchain craze. There was definitely a lot of blockchain projects in Haskell and hiring Haskellers and in that kind of space. And some of those still exist, like IOG, IOHK, whatever called now. But a lot of that stuff is like collapsed and I feel like often those kind of stories of things collapsing. I mean, have the AI winter and the fall of the Lisps. And I think you have similar things like when all these Haskell endeavors to do whatever stuff that yeah, can kind of burn the whole community. But yeah, I mean, I think there's a lot of factors involved, and I don't think it's the end for sure, but we're definitely not in the high point of oh, yeah, we're not at the high point at the moment, at least. But there's still stuff out there we can and hopefully we can increase and get more things happening. And there's other related things. I mean, at least for myself, there's definitely like a set of languages that I would be more or less happy working in. I don't think of Haskell even as I would say my favorite language. It is probably the one I write the most. But although at one point GitHub was telling me that Nix was the language I wrote the most, which was interesting. But yeah, I think it is the one I write the most. But definitely there's other languages that, at least in specific cases, I would pick. I feel like Haskell does a pretty good job of hitting a sweet spot though, with various trade-offs that make it appealing enough and good enough in terms of type system and ease of use and stuff like that. Yeah, so anyway, I do like it.
I've looked up a bit of Idris.
Oh yeah,
yeah, very
that's
nice.
a good one.
That's another nice one. Yeah.
Yeah.
Absolutely nice. Yeah, but that's just like if you think of a job market, Haskell is huge by comparison.
Yeah, compared to
Yeah, I know.
Yeah, and also the ecosystem is just very, very fun. But
yeah,
yeah, I mean the beauty of writing very dependently
yeah,
typed code in a language which is kind of all purpose. There's
yeah,
something
exactly.
about this. There's something about this so beautiful. And it has some of the features like the custom do that
You're right, right.
Idris came up with, I think, way earlier than Haskell did. I
Yeah,
remember.
there's definitely a lot of nice stuff. I don't think, yeah, I've never gotten paid to write Idris. I've written a bunch of it anyway. um, I did get paid to write Doll. That was good. It's a language I like a lot. But yeah, but yeah, yeah, no jobs. I don't know. That is a big Haskell complaint. Ugh.
Anyway, it's a bit late for me, so it's 1:30 a.m.
Yeah. Oh wow.
Oh
Yeah.
gosh, yes. Thank you very
So
much.
Yeah. Thanks for
Thank
joining,
you even
Enrico.
more for
Good to
joining us.
see
Wow.
you.
it was fun. I had fun. I like to push through it even if I'm busy. But I've understood a few things. Thanks. Thank you very much,
Cool.
Greg. Thanks
Yeah. Thanks for
everybody.
coming. Appreciate it. All right. See ya.
Yeah. Bye bye.
Well, yeah. So I maybe stop recording. So
Yeah. Sure.
Enrico froze for me actually.